Hello guys, so today I'm going to be talking about Gauss's law and how to find the electric field from a line charge. So we have a line charge that we'll denote by this line, and we'll put some charges here to denote what a line charge looks like. Now this line charge is going to have an electric field propagating around it all ways out, just like shooting all types of different ways. So we'll denote that electric field by these arrows. So that's our line charge, and this is our electric field around the line charge. Now we're going to have a point that is denoted by a distance r away from the line charge. So now we're going to go over to how do we calculate the electric field using r and also the charge density, which is for a line charge, it's going to be denoted as lambda. So lambda is the line charge. It's measured in charge per unit length. So Q over L. So this is our charge density, and this is R, the length away. So we're going to use the formula that this great guy came up with. It's denoted by so Gauss's law. It's denoted by Q enclosed. So that's E and C means enclosed. This is the charge. This is the charge inside of this shell. So there are different types of methods you can use to solve for this charge. So when we talk about Q, we're going to talk about Q, but it's inside of what we call a Gaussian surface. So this Gaussian surface, we're going to be using a cylinder. So this is the cylindrical method for Gauss's law. But you have to have some type of symmetric 3D shape or shape to use the law, and that it'll hold. So we'll be using a cylinder, and we'll denote the cylinder by this. And notice that the cylinder, it encapsulates everything, and that the point that we're finding is the radius of this circle. So very important point. And how, since we're calculating the charge here, the enclosed charge, which is like all along this line, this is Q. So now that we explain that, it's going to be over epsilon naught. And epsilon naught is a constant. It's the permittivity of free space. It's equal to 8.85 times 10 to the 12. And so this is equal to the closed surface integral of E, the electric field, dot dA, the area. So this is Gauss's law. Very, very cool equation to work with, guys. So to find the electric field, we're going to use, okay, so first we're going to be working with this equation, and we can write this out. You can write E out of the equation. We're going to be working with the right side, so we can write E out of the equation. So we can take that to the left side of the integral, and we can it's going to be times dA. So as I was saying before, how r is the radius of this, we're pretty much worried about, we're not worried about these two lids on the cylinder. We're worried about this inside, like what wraps around and what makes the cylinder on the side. So I mean, it's like this formula saves us a lot of time, because in order to calculate the charge at the spot, I mean, usually they, like back in the old days, they would have to add up, like sum up all the charges, the point charges on this line, and then calculate it for the electric field. But we can use this integral to calculate for the electric field. So this closed integral right here is equal to closed surface times dA. Now dA, since this is a circular type of thing and this is a length L, this is a length L. So since it's circular and it's given a length L, we can just denote this by E is equal to 2 pi r, which is it's kind of like the circumference of it's like circumference of a circle. So it's that, but then it's times L. So we have this. So this integral, like, I mean, we can mold this integral to what we want. There's really no integrating here when you know how, like, the whole area of, like, the formula of the areas that you want to use. So our area is going to be 2 pi r times L, and then it's E. So we have that, and we can use, this is going to be equal to this. So that's our equation. Now, if we were given the charge density, we can use that to calculate for E. So knowing the charge density is Q over L, we can say basically that we can substitute so we can substitute lambda times L for Q. So if we multiply by L, so basically, since this is charge over length, if we multiply by L, we get charge. So this is the charge. Now we can substitute this for Q. And when we do that, we get lambda of L over epsilon is equal to E pi r L. So, I mean, first thing you notice is the L's cancel. So we're left with lambda over epsilon naught is equal to E 2 pi r. So now we just have to rearrange for E, and we're basically done. So let me just make some room here. So we get E, electric field, is equal to, so if we divide both sides by 2 pi r, and we get, so we get, let's see, we get lambda over 2 pi r E naught. And this is the equation. So if you know the charge density, these are all 2 pi r, or actually just 2 pi is constant. If you know r, this radius, and charge density, you can calculate the electric field using Gauss's law. So yeah, that's pretty much it. This is Gauss's law using the cylindrical approach. Thanks.